The universe might be inside something much bigger. That sentence sounds like speculation. It is not. It is the logical consequence of precision measurements made by some of the most advanced scientific instruments ever built. For centuries, every expansion of our observational reach forced humanity to confront the same pattern. Reality was larger than we imagined. The Earth was not the center. The Sun was not unique. The Milky Way was not alone. Today we face a deeper shift. The observable universe spans roughly 93 billion light-years. That number is derived from light that has traveled for 13.8 billion years since the Big Bang, stretched by cosmic expansion. It forms a sphere around us, 46 billion light-years in every direction. But this sphere is not a boundary of existence. It is a boundary of visibility. In 2018, the European Space Agency's Planck satellite released the most precise map ever made of the cosmic microwave background, radiation emitted just 380,000 years after the universe began. By analyzing temperature variations measured in millionths of a degree, scientists determined the large-scale geometry of space. The result: the universe is flat within experimental uncertainty. According to Einstein's general relativity, a flat universe does not close in on itself. It does not curve like the surface of a sphere. If curvature exists at all, Planck data constrain its radius to be at least 250 times larger than the observable region. Within measurement error, the simplest interpretation is stark. Space may extend indefinitely. If that is true, then everything we have ever observed, every galaxy cluster, every supermassive black hole, every gravitational wave, occupies only a local patch inside a far greater expanse. Consider this carefully. All of recorded human history unfolded on one planet, orbiting one star inside one galaxy. That galaxy is one among hundreds of billions inside the observable universe, and the observable universe itself may be a minute fraction of what exists beyond our cosmic horizon. This conclusion is not drawn from philosophy or metaphysics. It comes from detectors cooled to fractions of a degree above absolute zero, from statistical fits with uncertainties expressed in multiple sigma, from independent measurements of cosmic structure, baryon acoustic oscillations, and background radiation all converging on the same geometry. If the universe is flat and extends beyond what we can see, then our entire cosmic map is incomplete by definition. The question is no longer whether something lies beyond the horizon. The question is how vast that unseen structure truly is. And in 1998, a discovery about the expansion of space itself would make that question impossible to ignore. In 1998, astronomers discovered something that should not have been possible. For nearly the entire 20th century, scientists believed the universe was expanding from the Big Bang, but slowing down. Gravity, the same force that pulls an apple to the ground and holds galaxies together, should have been gradually reducing the speed of that expansion. Two independent research teams set out to measure how quickly the universe was slowing. They used exploding stars called Type 1a supernovae. These explosions shine with nearly identical brightness, making them reliable cosmic distance markers. By comparing how bright they should appear to how bright they actually appeared, astronomers could measure how far away they were, and how fast space had expanded while their light was travelling. What they found was not a small discrepancy. The distant supernovae were dimmer than expected. That meant they were farther away than a slowing universe would predict. The only conclusion that fit the data was extraordinary. The expansion of the universe is speeding up. Not gradually, not recently. For billions of years, space itself has been accelerating outward. The statistical confidence of the discovery exceeded 5 sigma, the same threshold used to confirm the Higgs boson. The probability that this was a mistake was less than 1 in several million. Independent observations from the cosmic microwave background and large galaxy surveys later confirmed it. Something is pushing space apart. Scientists call it dark energy. To understand how strange this is, imagine throwing a ball straight up into the air. You expect gravity to slow it down. Now, imagine instead that the higher the ball rises, the faster it accelerates away from you. That is what the universe is doing on the largest scale imaginable. Dark energy now accounts for roughly 70% of the total energy in the universe, yet its measured density is astonishingly tiny, about 10 to the power of minus 29 grams per cubic centimetre. That is equivalent to only a few hydrogen atoms spread across a volume the size of a refrigerator. And here is where it becomes mind-bending. Quantum physics predicts that empty space should contain energy, vacuum energy. But when physicists calculate how much, the result overshoots what we observe by 120 orders of magnitude. That is a number so large that writing it out would require more digits than there are atoms in your body. If the theoretical value were correct, the universe would have expanded so violently that galaxies could never have formed. Stars would not exist, neither would we. Instead, we find ourselves in a universe where expansion is accelerating, but gently enough for structure and life to emerge. The stakes are enormous. If vacuum energy can, in principle, take different values, then perhaps our universe is not the only region where physics unfolds. Perhaps it is one domain among many, each with different properties. The acceleration of space does more than shape the future. It hints that our universe may be part of something larger. To understand how that larger structure might form, we must go back to the very first fraction of a second after the Big Bang, when space itself expanded faster than light. Before galaxies, before atoms, before light could even travel freely through space, something happened. In the early 1980s, physicist Alan Guth proposed a radical idea to solve a growing crisis in cosmology. The universe, according to observations, was too smooth. Regions separated by billions of light years had nearly identical temperatures, even though they were never close enough to exchange information at the speed of light. It was as if two cities on opposite sides of the planet had the exact same weather pattern without ever communicating. This became known as the horizon problem. Guth's solution was simple in concept, but staggering in consequence. He proposed that in the first tiny fraction of a second after the Big Bang, around 10 to the power of minus 37 seconds, the universe underwent an episode of exponential expansion. Space itself did not just grow, it exploded outward. During this period, it may have doubled in size roughly 60 times in a vanishingly small interval. To grasp the scale, imagine something smaller than a proton expanding to macroscopic size almost instantly. Inflation would have increased the size of the universe by at least a factor of 10 to the power of 26. This expansion smoothed everything out. Regions that now appear unimaginably far apart were once compressed into a tiny uniform patch before inflation stretched them beyond each other's reach. The theory made a bold prediction. Quantum fluctuations, tiny random variations in energy at microscopic scales, would have been stretched to cosmic size. Those fluctuations would leave faint imprints in the cosmic microwave background radiation. Decades later, satellites such as WMAP and the European Space Agency's Planck mission measured those patterns. The fluctuations matched inflation's predictions with remarkable precision. The spectrum was nearly scale invariant, exactly as inflationary models suggested. Inflation solved the horizon problem. It explained why the universe is flat. It accounted for why we do not observe exotic relic particles predicted by earlier theories. But hidden inside the mathematics was something even more profound. If quantum fluctuations drive inflation, then inflation may not stop everywhere at once. In some regions it ends, forming a universe like ours. In others it continues. That means our universe may not be the whole product of the Big Bang. It may be one region where inflation stopped. And beyond our cosmic horizon, inflation could still be unfolding. To follow that possibility, we must examine what happens when inflation never fully ends. What if the Big Bang was not a singular event? In the mid-1980s, as physicists refined the mathematics of cosmic inflation, an unexpected conclusion began to surface. Andre Linde, building on Alan Guth's original proposal, realized something unsettling. Inflation does not naturally shut off everywhere at the same time. Quantum physics makes that almost impossible. Inflation is driven by a field, often called the inflaton field, whose energy causes space to expand exponentially. But quantum fluctuations disturb that field. In some regions, the energy drops, inflation ends, and a hot Big Bang begins. In other regions, fluctuations push the field higher, and inflation continues even faster. The result is not one expanding universe. It is a cosmic process that never completely stops. This framework became known as eternal inflation. Imagine boiling water. Bubbles form in different places at different times. Each bubble grows independently. Now, replace water with space itself. Replace bubbles with entire universes. In this picture, our observable universe is not the whole outcome of inflation. It is one bubble where inflation ended roughly 13.8 billion years ago. Beyond our cosmic horizon, inflation could still be unfolding, creating other regions where space stops inflating and forms new universes. The mathematics is difficult to avoid. Once inflation begins, the volume of inflating space grows faster than the rate at which inflation ends. Even if bubble universes form constantly, the background inflation expands even more rapidly. Over time, the inflating region dominates. The stakes are staggering. If eternal inflation is correct, then what we call the universe may be only a local pocket inside a vastly larger inflating structure. Each bubble could have slightly different physical conditions depending on how the inflating field decayed. Some researchers have searched for evidence of collisions between bubble universes, subtle circular imprints in the cosmic microwave background radiation. Analyses of Planck satellite data have produced intriguing but statistically inconclusive hints. No signal has yet crossed the threshold of decisive confidence. But the theoretical implication remains. Our Big Bang may not represent the beginning of everything. It may mark the moment inflation stopped in our region. Beyond our horizon, space may still be inflating, endlessly generating new cosmic domains. If that is true, then the question shifts. Not how big is our universe, but how many universes are forming within something far greater. To confront that possibility, we must examine why the laws of physics in our universe appear so precisely balanced. If our universe is one bubble among many, there is a question we cannot avoid. Why does it look so precisely calibrated for structure to exist at all? Throughout the 20th century, physicists identified roughly 30 fundamental constants that define the behavior of reality: the strength of gravity, the charge of the electron, the rate of cosmic expansion. These numbers are not predicted by current theory. They are measured, and they appear extraordinarily specific. Consider gravity. If it were slightly stronger, stars would burn hotter and exhaust their fuel in millions of years instead of billions. Complex chemistry would never have time to emerge. If it were slightly weaker, gas clouds might never collapse to form stars at all. The strong nuclear force, the force that binds protons and neutrons, must lie within a narrow range. Change it by about 2%, and either only hydrogen exists, or nearly all hydrogen fuses into heavier elements in the early universe. In one case, no complex atoms. In the other, no long-lived stars. But the most extreme example emerged after the 1998 discovery of dark energy. The cosmological constant, the energy density of empty space, must fall within an astonishingly narrow window. If it were even 1,000 times larger than observed, cosmic expansion would have accelerated so violently that galaxies could never form. If negative and moderately stronger, the universe would have collapsed long before stars ignited. The observed value is tuned to roughly 1 part in 10 to the power of 120 compared to naive quantum field theory predictions. That is not a small adjustment. It is a cancellation so precise it has been called the worst theoretical prediction in the history of physics. In 1987, Nobel laureate Steven Weinberg made a bold argument. If many universes exist with different values of the cosmological constant, observers would only arise in the rare regions where that value permits galaxy formation. He predicted that if this reasoning were correct, we should observe a cosmological constant just small enough to allow structure, but not dramatically smaller. A decade later, the accelerating universe was discovered. The measured value matched Weinberg's anthropic estimate within an order of magnitude. This does not prove a multiverse, but it changes the stakes. If eternal inflation produces countless bubble universes, and if each bubble settles into slightly different physical conditions, then our universe's apparent fine-tuning may not be a miracle of precision. It may be a consequence of selection. In that case, the laws of physics we observe are not uniquely fixed. They are environmental, and that possibility forces an even deeper question. If physical constants can vary across cosmic domains, what determines the underlying framework that allows such variation in the first place? To approach that question, we must shift perspective from matter and energy to information itself. What if the universe is not three-dimensional at its most fundamental level? In the 1970s, physicists studying black holes uncovered a result that should not have been possible. Jacob Bekenstein and Stephen Hawking discovered that a black hole's entropy, a measure of its information content, does not scale with its volume, it scales with its surface area. That detail was not mathematical trivia. In ordinary systems, information increases with volume. A larger box can contain more particles, more configurations, more entropy. But a black hole behaves differently. Its maximum information is proportional to the area of its event horizon. This observation led physicists Gerard 't Hooft and Leonard Susskind in the 1990s to propose something radical, the holographic principle. The principle states that the maximum information contained inside any region of space is determined not by its volume, but by the area of its boundary. In other words, the three-dimensional world we experience could be described entirely by information encoded on a distant two-dimensional surface. In 1997, theoretical physicist Juan Maldacena provided the first concrete mathematical realization of this idea. His work on the ADS/CFT correspondence demonstrated that a higher dimensional gravitational system can be exactly equivalent to a lower dimensional quantum field theory on its boundary. Gravity in the bulk, quantum physics on the surface. Two seemingly different descriptions. One identical reality. The implications are profound. If a similar principle applies to our universe, then everything inside our observable horizon, galaxies, black holes, even space and time themselves, could emerge from information encoded on a boundary far beyond our direct access. The maximum information capacity of our observable universe is finite, roughly 10 to the power of 123 bits, determined by the area of the cosmic horizon measured in Planck units. That number is staggeringly large, yet it is not infinite. This suggests that space is not infinitely detailed. It has a fundamental information limit, and if space is emergent from quantum information, then the universe may not simply sit inside something larger. It may be generated from something deeper. Experimental tests remain indirect. Searches for holographic noise in ultra-precise interferometers have so far produced null results, placing constraints on simplified models. Extending holography to our expanding universe remains an open challenge, but the theoretical convergence is striking. Black hole thermodynamics, quantum gravity, string theory, independent lines of research all hint that the fabric of reality may not be fundamental, but encoded. If that is true, then the question shifts again. Not only what lies beyond our horizon, but what lies beneath it. To explore that foundation, we must descend the smallest scale physics allows, where space itself may dissolve into quantum fluctuations. In 1955, physicist John Wheeler proposed a radical idea while attempting to reconcile quantum mechanics with Einstein's theory of gravity. At extremely small scales, around 10 to the power of minus 35 meters, known as the Planck length, space would no longer be smooth and continuous. It would fluctuate violently. He called it quantum foam. At everyday scales, space feels stable and predictable. Planets orbit, light travels in straight lines. Geometry behaves consistently, but quantum mechanics insists that nothing is perfectly still. Energy fluctuates constantly, even in empty space. At the Planck scale, those fluctuations would become so intense that they distort space-time itself. Tiny wormholes could briefly appear and vanish. Microscopic black holes might flicker into existence and evaporate almost instantly. The smooth fabric described by general relativity would dissolve into probabilistic turbulence. This is not science fiction. It is what current equations predict when gravity is treated as a quantum phenomenon. The stakes are enormous. If space is fundamentally discrete or fluctuating, then the universe we observe is not continuous at its core. It is an emergent average, like a calm ocean surface hiding chaotic molecular motion beneath. Physicists have attempted to test this indirectly. High-energy gamma-ray bursts from distant galaxies serve as natural probes. If space has a granular structure, photons of different energies might travel at slightly different speeds over billions of light-years. Sensitive detectors have searched for these dispersion effects. So far, no deviation has been observed. These null results rule out many simple quantum gravity models, tightening constraints on how space might behave at the smallest scales. Future gravitational wave observatories, such as the Laser Interferometer Space Antenna planned for the 2030s, may probe even deeper, searching for subtle departures from classical predictions. Despite the absence of direct evidence, the theoretical necessity remains. General relativity and quantum mechanics cannot both be fully correct at the Planck scale without modification. A deeper framework must exist. If space-time emerges from something more fundamental, from quantum geometry or informational structure, then our universe is not built on solid ground. It is built on a deeper substrate. And if that substrate extends beyond our cosmic horizon, then what we call the universe may be only a large-scale manifestation of a far more intricate architecture. To understand how that architecture might extend beyond 3 familiar dimensions, we must consider a possibility once confined to theory, that additional dimensions of space may exist beyond those we perceive. What if our entire universe is not the whole of space, but a surface inside something larger? In 1999, physicists Lisa Randall and Raman Sundram proposed a model that challenged one of the deepest assumptions in physics, that the 3 dimensions we experience are all that exist. Their work, building on developments in string theory, suggested that additional spatial dimensions may be real, but hidden from direct detection. The idea is known as brane cosmology. In this framework, our universe is a 3-dimensional brane embedded within a higher dimensional space called the bulk. All the particles and forces described by the standard model, electrons, quarks, photons, would be confined to this brane. They cannot leave it, just as ink cannot escape the surface of paper. Gravity, however, may behave differently. In these models, gravitons, the hypothetical carriers of gravitational force, can propagate into the extra dimension. If gravity spreads out into higher dimensional space, it would appear weaker within our universe. That weakness is not small. Gravity is approximately 10 to the power of 36 times weaker than electromagnetism. This enormous disparity, known as the hierarchy problem, has long puzzled physicists. Brane models offer a possible explanation. Gravity is not inherently weak. It is diluted across extra dimensions. The stakes extend beyond theoretical elegance. If additional dimensions exist, they could reshape our understanding of cosmic structure. Massive objects in nearby branes could exert gravitational influence on our universe without emitting light. Some theorists have even explored whether dark matter might reflect gravitational effects, leaking from adjacent branes. Experimental tests are underway. The Large Hadron Collider has searched for missing energy signatures that would indicate gravitons escaping into extra dimensions. So far, no such evidence has appeared. These null results impose strict constraints on how large or accessible extra dimensions could be. Yet the possibility remains open. String theory, one of the leading candidates for quantum gravity, mathematically requires additional dimensions for internal consistency. In many formulations, space contains at least 10 dimensions. The extra dimensions may be compactified to scales too small to observe directly, or they may be warped in ways that hide them from conventional detection. If our universe is a brane, then what we perceive as total reality is a slice of a larger geometric structure. Other branes could exist parallel to ours, separated by distances imperceptible to us, yet vast in higher dimensional space. Entire universes could float nearby, gravitationally adjacent, forever invisible. If that is true, then our universe is not simply expanding into emptiness. It exists within a higher dimensional framework whose full structure we cannot yet see. But dimensions alone may not tell the full story. To understand whether our universe could be one phase within a larger cosmic cycle, we must examine a theory that challenges the very beginning of time itself. For nearly a century, cosmology has traced the history of the universe back to a hot, dense origin 13.8 billion years ago. Space expanded, matter cooled, galaxies formed. The timeline seemed clear. But in 2010, Nobel laureate Roger Penrose advanced a radical alternative known as conformal cyclic cosmology. His proposal challenges a fundamental assumption that time itself began with the Big Bang. Penrose's idea begins with a simple observation. In the far future, trillions upon trillions of years from now, all stars will have burned out. Black holes will evaporate through Hawking radiation. Matter will decay. The universe will consist almost entirely of radiation, particles with no rest mass. For massless particles, time behaves differently. Without mass, there is no intrinsic clock. Penrose argued that this extremely distant future, where only radiation remains and distances lose physical meaning, can be mathematically rescaled. Through a conformal transformation, the infinite future of one cosmic phase can be mapped onto the Big Bang of another. In this view, our universe is one aeon in an eternal sequence. The end of a previous cosmic era became the beginning of ours. There was no singular creation event, only transition. The stakes are profound. If correct, the Big Bang was not an origin point, but a boundary between cycles in a much larger temporal structure. Time did not emerge from nothing. It extends infinitely, forward and backward, through successive aeons. Penrose and collaborators searched for evidence in the cosmic microwave background. They proposed that violent events from a previous aeon, such as collisions between supermassive black holes, could leave faint circular imprints in our CMB data. Analyses of Planck satellite maps revealed candidate patterns. However, most independent studies concluded that the statistical significance was insufficient to rule out random fluctuations. The debate remains open. Even without confirmed evidence, the conceptual shift is immense. If universes can follow one another in endless succession, then our cosmos is not merely embedded in larger space. It may be embedded in a larger history. A history without absolute beginning. Across inflation, holography, extra dimensions, and cyclic cosmology, a pattern is emerging. Each theory, from a different angle, suggests that what we call the universe is not the final layer of reality. To understand what that larger structure might ultimately imply, we must step back and confront the full convergence of modern physics. After more than a century of modern cosmology, a quiet but profound realization has taken shape. The universe we observe may not be the whole of reality. This conclusion does not arise from speculation or philosophical preference. It emerges from independent lines of evidence, geometric measurements, quantum theory, gravitational physics, and precision astronomical observations, all pointing beyond the visible horizon. In 2018, the Planck collaboration confirmed with extraordinary precision that the large-scale geometry of space is flat within observational uncertainty. Under Einstein's general relativity, a flat universe does not curve back into itself. It extends indefinitely, or at the very least far beyond the 93 billion light-year sphere we can observe. That observable region is not an edge. It is a limit imposed by the finite speed of light and cosmic time. 2 decades earlier, in 1998, independent supernova surveys demonstrated at greater than 5 sigma confidence that cosmic expansion is accelerating. Dark energy dominates the energy budget of the cosmos, yet its measured value differs from naive quantum predictions by 120 orders of magnitude. Such a discrepancy suggests either an unknown mechanism or a broader framework in which vacuum energy can vary. Inflation theory, first proposed in the 1980s, resolved major cosmological puzzles and predicted the precise fluctuation patterns later observed in the cosmic microwave background. Yet the mathematics of quantum fluctuations implies that inflation may not end everywhere at once. In that case, our universe would represent a local region where inflation stopped, surrounded by an inflating structure far larger than what we can see. Black hole thermodynamics revealed that information scales with surface area rather than volume, inspiring the holographic principle and the possibility that space itself is emergent from deeper informational laws. String theory and brain cosmology introduced additional spatial dimensions, suggesting that our universe could be embedded within a higher dimensional bulk. Conformal cyclic cosmology proposed that even the Big Bang may not mark an absolute beginning, but a transition between cosmic epochs. Individually, these frameworks remain incomplete and actively debated. Collectively, they share a common implication. The observable universe is a local domain within a larger structure. The constants we measure may not be universally fixed. The beginning we infer may not be ultimate. The geometry we observe may be only a slice of a far deeper architecture. Modern physics has not yet revealed the full structure beyond our horizon, but it has narrowed the possibilities with increasing precision. Across geometry, quantum mechanics, gravity and cosmology, a pattern continues to emerge, one supported by data, constrained by mathematics, and refined by decades of inquiry. Scientists think the universe might be inside something much bigger, not as metaphor, not as fantasy, but as a serious scientific possibility, one that may redefine our place in reality itself,